There are some applications of vectors in physics in which we care whether or not the vectors are pointing in the same direction. Now, we've talked about work. Let's say we have a box and we want to displace it in a certain direction. Well, we're using a force to do that displacement, and we are interested in how much of the force is pointing in the same direction as the displacement vector. Let's say we would like to open a door. Now, you've most certainly opened a door many times in your life, and you've realized that there are two important things to go about doing this. There is the position at which you apply a force, and then there is the force that you apply to the door. Now, you know that applying a force directly in the same direction, either pushing the door on its side or pulling the door on its side, isn't going to have a lot of impact. The optimal is when you are perpendicular to the door. There's an angle between the force vector and this position vector, and that angle is in there. We are interested in the portion of the force that is perpendicular to the door. This led physicists to talk about a new idea called torque. Torque is a vector, and physics people decided that two sizes are important. There's the size of the position, how far away you are from the pivot point or the hinge, and then there's the portion of the force that is perpendicular. And we are interested in this portion, and that's related to the sine of the angle between the vectors. Another way to visualize this is if we have our position vector like this, and we apply some sort of force, then the angle here, that is the perpendicular component. The size of this torque vector is the size of that position vector, the size of the force vector, times the sine of the angle between them. The direction is something that we are interested in here. If we had our position vector like this, and we had our force vector, then the torque vector would be perpendicular to both. Now, two vectors fit this bill. You could have one pointing up or one pointing down. So physics people decided that they would use the right-hand rule when talking about this vector. The fingers point in the direction of R, they curl in the direction of F, and then the thumb points in the direction of this result. When we generalize this, we come up with a new vector product called the cross product. And I'm going to call this the geometric definition of the cross product. Given two vectors, A and B, that live in R3, we're going to define the cross product of those two vectors as this new vector AXB, and that X is going to represent the cross product. This is a new vector that has a size, magnitude of one vector, magnitude of the other vector, and the sine of the angle between them. There's A, there's B, there's the angle between them, and then the direction follows the right-hand rule. If you curl from A to B, your thumb will point up, and there is the vector A cross B. A cross B produces a vector, whereas the dot product A dot B produces a scalar. From this geometric definition, we can come up with some basic properties. For example, if I ever wanted to take the cross product of a vector with itself, the angle between the two vectors is 0, the sine of 0 is 0, and that means that the size of this cross product vector is 0. If you have a vector with a size of 0, then the only vector that can produce a size of 0 is the 0 vector itself. A vector crossed with itself is 0. And this is a test for being parallel. If we had two non-zero vectors and we took their dot product and they produced a 0, that told us the vectors were perpendicular. If you take the cross product of two vectors and they are not zero and they produce the zero vector, that means the two vectors are parallel. Another important property has to do with the order in which you take the cross product of two vectors. So for example, if B cross A, this is the vector B and this is the vector A. If I follow the direction of the right-hand rule, I would have a vector that points up like this. There's B cross A. The size of this vector has to be size of the first, size of the second, sine of the angle between them. Well, there's nothing preventing me from writing this in the opposite order like that. The angle between the two vectors is always the same. So this tells me that it's exactly the same size as A cross B. The direction is the only possible difference. All that would change is that the answer would point down. So there would be A cross B. If you were to switch the order in which you take the cross product of two vectors, all it does is change the direction. Another useful result is to do with area. If you had two vectors, like so, there's an angle between them. The length there would be B sine theta. If we were to draw a parallelogram, then this component is a triangle, and it's exactly the same shaped triangle as we had above. So that means that the area of this parallelogram is just the length of the bottom vector times the height. It would essentially form a new rectangle, just like this. And this area then would be AB sine of the angle between them, which is just the length of that cross product vector. Now, some very important common examples has to do with the basis vectors, I, J, and K in R3. The length of each one of these basis vectors is just 1. If we take a right-handed coordinate system where this is x, this is y, and this is z according to the right-hand rule, the vector I is a unit length vector that points this way, j is a unit length vector that points that way, and k is a unit length vector that points this way. If you take the cross product of a vector with itself, you will simply get 0. So the cross product of each of these unit vectors with itself should be 0. If I were to say I crossed j, I would get a vector that has to have a size. It would be the size of I, size of j, sine of the angle between them. Well, the angle between them is pi over 2, so that's a 1. This would give me an I crossed with the j times a 1, which would just give me a 1. So there's its size. Its direction has to be in the k direction, according to the right-hand rule. And then the only option is that I crossed with j has to be equal to k. Now, by this similar logic, if I wanted to go I crossed with k, according to the right-hand rule, the result would point in the negative y direction. The size of the vector would still have to be 1 because the angle between I and k is pi over 2, and the only vector that would fit the bill here would be negative j. If I went j crossed with k, I would have to produce a unit length vector in the x direction, which would give me I, and if I went k cross I would have to produce a unit length vector in the y direction, so that would have to be j. If I went through and I went j cross I would get negative k. I'd point in the opposite direction, and k cross j would be negative I. So there's a wonderful little way to remember this. If I take the three vectors and I write them in clockwise direction, if I follow the clockwise direction, all of the results will be positive. I crossed with j produces k, j crossed with k produces I, K crossed with I produces J. But if I take those same three vectors, I, J, K, alphabetical order, but go the other way, if I go counterclockwise, I'll get the negative result. I crossed with K is negative J, K crossed with J is negative I, J crossed with I is negative K. Now, unfortunately, we are going to run out of mileage with the geometric definitions. The geometric definition is not precise. We are going to struggle to come up with useful properties and ways of working with the geometric definition. That means what we need to do is extend the geometric definition to an algebraic one. We need an algebraic definition of the cross product. The next video will walk us through how to come up with that algebraic definition.